Right. Yeah, it's kind of funny that it's
Front row on this side of the room. I'm wondering what about that? The other thing I've noticed about
Microphone.
You gotta stay next to the podium now.
How's this? Better? Oh, no, that's fine. That's fine. The other thing that's kind of unusual is that in this group of people, we have a lot of white men, and there's nothing wrong with that. Like, I love men, but there. I wish some did. There's maybe it's easy as a person who is a person of color or a woman or somebody who's intersex to look at a culture made up of people who look different from you or come from a different background and identify a common cultural aspect like drinking or inside jokes and to view that as being in some way exclusive. None of this is necessarily wrong, but I think it bears considering maybe how we reflect ourselves to outsiders who are part of us. That's completely unrelated to what I'm here to talk about. I do this thing called Riemann. My name is Kyle Kingsbury. I work at this company called Factual, and I've only been there for a week, so I can't really tell you what I do there. What I was doing before Factual for 6 months was working full-time on this open source project. And I'm hoping to kind of explain a little bit about why I did it, to justify this insanity to other people, in the hopes that maybe some of you will join in. First, a story, not about work, but what happens outside of work. What happens at 2 in the morning when, like, good people were sleeping. And if you're like me, you sleep with your phone, sort of bundled up underneath the bed, and it goes off. And you reach down, to pick up this obelisk, and you hold it to your head, and it whispers to you in the voice of the Oracle of Delphi, this gravelly provenance of the future. It says, PagerDuty alert. You have 3 unacknowledged incidents on service, Nagios. I think, is that the canonical pronunciation now because of PagerDuty? The question arises, what is it that you do at this point? Like, your night is ruined, you're bleary-eyed, you pull out your laptop, and you're going to be staring at it for hours, however long it takes to fix this problem. And you've got 3 principal things in your mind. The first one is, oh God, why me? The second one is, what even is the internet? Like, why? Now that I'm being paged for this thing, what happened? And then the third one is like bringing online all of the goo forward of the lizard brain, the stuff that analyzes problems and thinks about cause and effect. And when you don't have that analytical part of your brain online, mistakes are made, mistakes which must be later faced in the uncompromising light of day. Mistakes with tab completion, mistakes where you balance services that had nothing to do with the actual problem because it seemed like a good idea at the time, you end up creating more issues than you fixed. We're never going to make perfect software. We're always going to have operational challenges and people will always be on call. But if we put a little bit of work up front into instrumenting our systems, into designing them in a way that makes them more robust to failure and easier to understand when they do fail, then we can reduce the need for anything above the lizard brain, which is so hard to get online at 3 in the morning. The military and boundaries, as a matter of fact, is really big on this idea called the OODA loop, where you observe and then you rotate 90 degrees and you orient and you continue rotating as you decide on what to do and you act. In practice, I think this can be maybe a little more general of a process than actually applies to problem solving. It's like, well, the site's on fire, there's your orientation, now decide what to do with that. I tend to ask a more specific set of questions of myself. I ask, what's really broken? I've got this alert. I've got probably 40 or 50 alerts, and I need to figure out which one of them is salient. Where did the failure occur? Right? Is it a node? Is it a service? Is it some sort of clustered thing? And if multiple things happen, because usually you've got a whole chain of causality in a pipeline, what was the root cause? Right? Which one happened first and caused the rest of the stuff to break? You have to bring context to the situation. Context that lives in your head, context that lives in your ops playbook. Once you've figured out a particular part of the problem you can address, you determine an observable. Right? My background's in physics, actually, and I spent a lot of time doing time series analysis. And one of the things you learn is that modeling systems with mathematics, right? Like we'll just throw Tyson at the problem. It's a time series analytics package, and it will tell us about autocorrelation. It will allow us to extract dimensionality and project phase spaces out of time series data. Well, it turns out that that involves like basically hand tuning a bunch of parameters to your particular data set, and you do it like for hours and years of your life. And it turns out to be really difficult to generalize to other people's problems, which is why I'm somewhat skeptical of this stuff. I think the role of monitoring should actually be to augment human intelligence as much as possible, and then maybe some really common problems we can solve with machine intelligence. So what you do is you localize the problem, and you determine some observable, something you can watch, like the Nagios alert, and then you make a change. You bounce a service, you adjust a queue, you remove some files, and then you wait. You have to wait because if you make two changes at the same time, you don't know which one of them actually fixed the problem. So if your Nagios poller runs every minute or every 5 minutes, you have to wait a mean of 30 seconds or 2.5 minutes before you can do anything else. So you make a change, wait 2.5 minutes, make a change, wait 2.5 minutes, and before you know it, you've used up the whole morning. This suggests that it should be really important to us to shorten the loop, to have data that cycles as quickly as possible so that you can identify the consequences of your actions quickly. Once you fix that particular part, you need to regeneralize. You look at the whole system and you figure out where the problem is now. So you're always localizing, and then you're fixing that problem. You expand, localize, contract, expand, contract. And when I talk about this expansion and contraction or localizing a problem, I'm talking about a space, right? Obviously, your operating system is not like in front of me in the cloud. It's somewhere on computers. And so we need to talk about what is the shape of monitoring space? Like if we had a topology for operations, what would it look like? I argue that there are sort of two physical dimensions to where is the problem. There is a physical dimension, right? A problem occurs in a particular node or particular cluster. And then there's a logical dimension, like it was a problem with a particular queue, or it was React's get latencies were above a certain threshold. So there's both a logical and a physical dimension. Maybe they could be nil. They are countable, right? There's a fixed number of things in the universe, and you can point to them and number them out. So they're discrete in that sense, even though there could be an infinite number. And we also have some structure we can impose, right? Like you can structure hosts using the domain name, right? So you can have like hierarchy and grouping, and you can do the same thing for logical services, right? Like JMX establishes like this four-dimensional partitioning of logical service names. Graphite, right? They use dots to separate these dimensions, but you can really think of them as being just two axes on this graph. And then the other question, right? When? When did this thing happen? If you take a square in that graph and you pull it up in time, you get this volume, right? Like a cube, a rectangular solid, I guess. And if you do that to all of your services over time, you get this whole field, like a volume, defined by host, service, and time. You can think about the total evolution of your data center, all the stuff you do, as being this giant volume full of little voxels. I borrow this terminology from special relativity, where the universe is considered to be made up of an infinite number of events, all of which have these space-time coordinates. In our cases, the event is sort of the quanta of the monitoring field. It's specified uniquely by a host, right, like www1, a service like memory use, and maybe a temporal coordinate saying this event started at 3:18:20 a.m. And typically it has some time extant that it's valid for. So you'd see a bunch of events overlapping, and each one might be valid for a second or a minute or however long it is that your polling interval is, such that you have continuous knowledge of the state out of this discrete set of events. The events also have some state associated with them, other dimensions, things like a metric, maybe some number that is associated with the service at that point in time, 1.35 gigabytes or 1.35 requests per second. You could have a state, okay, warning, critical, right? Nagios does that. Maybe some tags to establish a taxonomy, a description to tell you more about what happened, like a service output. And then any other keys and values you'd like. These events aren't particularly interesting in isolation, but if you've ever played Minecraft, you'll know that putting together simple blocks in large fields can actually be really cool. You can get contextual information. The relationship of the events tells you something about the service. And then I think it's our job to construct narratives. Zach Tellman gave a really good talk last week at Closure West entitled Code Execution as Data, where he makes this argument in full. But I assert that when you're trying to understand a problem or trying to optimize a system, you're really telling yourself a story, a narrative about a particular pathway through this space, that this thing failed and it led to a failure here and this latency was involved, or we could fix this particular aspect of the system and that's our bottleneck. And we visualize the system in different ways to understand that. if you take descriptions and you list them out in time and scroll it, you get tail-f. That's how we understand one particular system and its operation in detail. If you wanted to understand the relationships between multiple services, you might draw them out, say showing their state over time. And then you could see something like a cascading failure appearing as a stair step. If you wanted to spatially locate something, to understand at this particular moment in time where are the failures, you could plot out hosts and services in 2 dimensions, and maybe fill in a state or a metric in color or size, density, that sort of thing. So this helps you answer that question about where. And the question of when, we have a spatial projection for that too, right? That's time series graphs. You can project metric versus time and maybe show multiple series, and you can use small multiples, right? Tufte has shown us a lot of ways to work time series. And you can get really fancy, right? You can define phase space observables, dimensionless quantities in your system. Riemann's job in this theoretical context is to help you construct those narratives, to allow you as an operations engineer to carve and mold this world of events and all the logs and all the crazy stuff your infrastructure is doing into interpretable, actionable stories, actionable events. And it does that with Lisp. If you're familiar with John Murali, J. Recurse's famous comic about using Erlang MapReduce jobs to query a database, you might be asking the very same question of me. Do I honestly expect you to use Lisp to instrument your systems? The answer is maybe. Actually, can I get a show of hands? How many people here have used Riemann? Holy cow, that's cool. So like, I have 600 stars on GitHub, and I have no idea what that means. This is like drive-bys, like that was cool, or is it people who actually use it? I have no usage data. So if people happen to hop in a channel and like give me a note saying they like it, or they're using it, or they want something, that'd be neat. So justification, right? I want to tell you a story about you as a web server. If you're a web server, you process a request, and you emit an event saying, hey, I handled this thing, here's how long it took. It was HTTP 200, maybe. And you drop it into the network, and the network is a vast ocean full of currents and swirling things and sharks, and it floats along for a while, and it gets sucked up by Riemann and joined together with all the other events in your system that are coming in via TCP and UDP. They're serialized protocol buffers. So it gets jumbled together with a bunch of other events about system health and business metrics, how many dollars you're making per minute, signups, whatever else you like. And at some point, it gets filtered out. A special fork in the stream sucks this thing away, and it joins up with all the other web request events. And then they fall over the edge of a chute. They fall onto this water wheel, and the heavier the events are, the bigger the metric, and the more events per second that fall through, the faster the wheel turns, right? So you can think about this sort of rate mill as giving you the flux of HTTP requests. And that those flux events, every few seconds they say, oh, here's how many requests per second we processed, or here's what our latency was. Those events get stamped by a large machine. They're loaded into a sort of tunnel, and the tunnel moves a little bit, and it turns out to be a gun, and it fires, and the event launches into the atmosphere, burns into space, and it flies over and hits planet Graphite at 1,000,000 miles an hour. And that is where your time series data comes from. So that's the life cycle of an event, and I want you to do this 1,000,000 times per second. If you think about that arrangement of streams, right? You can think of it like a physical stream. These events sort of bobbing along, going through special machines, and maybe those forks in the canals are actually like hyperdimensional or whatever. But it's okay. We can pretend. But that's also all like a tree, right? Streams goes to where, goes to rate, goes to graphite. We've filtered, we've taken a flux, and then we forward it onto another system. And you could say, well, how do I represent trees in software? How do I write this configuration? And the canonical answer, of course, is XML. Oh God, don't make me use Maven. So there's another way to represent trees, and that's S expressions. If you could just surround each node in the tree with parentheses, and you would get this representation. Our streams, see tree, S expression. Tree, S expression. Same thing. The difference is the S expression is also executable code. If you write this down in your config, it's a program, it's a function, and you can run it. Specifically, events in Riemann are just represented as maps. Objects in Ruby or hashes. Sorry, hashes in Ruby, objects in Java. And then streams are just functions which take an event and do something with it. So when you call rate 5, it constructs one of those little mills. It's a function which takes an event and then it does some stuff. So most of the stuff you see in Riemann is constructing these anonymous functions. They carry along some state and they do some sort of transformation, and they forward other streams deeper in the tree. This means that stream composition is just function composition, and we can use all of the weapons that we have at our disposal for dealing with functions, in code, to organize the problem of stream composition, to organize the narrative. If you want to define a new operation, something that doesn't exist in Riemann, it tends to be possible. Not that it's necessarily easy, right? Because dealing with like concurrent state is never an easy problem, but you can at least do it. And a lot of times, the primitives that I give you in Riemann will plug together in nice ways to form new tricks. If you have a derivative operator like DDT that says every 10 seconds take the derivative of the metrics and then emit a new value with that. If you take the derivative once and you take it again, you get a second derivative. And with that, I'd like to introduce you to all sorts of cool streams. Filtering, we've already seen. You can say where state error. That says wherever the state of the event is equal to the string error, go ahead and send it to my children. But you can get fancier. You can do arbitrary expressions here. So where the service is not special and where the state is exception. And you can use regular expressions. Where the service begins with the word Q and metric lies between 5 and 15. One of the advantages of prefix notation is that ordering comparators become really simple. You can then say, okay, where these conditions are met, go ahead and email this person and also trigger an event in PagerDuty. Getting a little complicated, that stream you can think of as an if statement, right? It's like a filter, like a barrier, a grate you install in the sewer. But you could also fork. And if you wanted to fork, you can include an else clause in your where. And then you can route everything that matches the predicate to one stream and everything that doesn't match to another stream. You might be asking about switch statements. New in Riemann 0 to 0, you've got split. You can apply a whole bunch of different expressions. Where the service is foo, go to foo. Where the state is bar, go to bar. When the metric is 3, go to baz. And then fall through to some default stream. Or if you wanted to split on a particular value, you can use split p. This one compares on the metric. You split, based on the metric, into 3 different branches, one for greater than 95, one for greater than 0.8, and one that's okay. And then you reconverge all of those in the index. The index's job is to give you the current state of the system in Riemann. It's a hash table showing you the most recent event for each host and service received. So you can imagine slicing through that event field with a sort of invisible plane that's always rising in time. That's the index. It's a lot like Nagios's service grid. We've already seen how to filter, but you can also change these events. If you say with service HTTP request rate, it assigns a new service to a copy of the event and then forwards it to PRN, which is a built-in closure function that just prints. So this is a way to print. You can imagine like assigning, sort of dropping a die into the stream, and it sort of colors everything that goes downstream at that point. Because closures data structures are all immutable, you can actually not have to worry about changing the underlying object, right? These are all thread safe. Everything is run concurrently in parallel. It scales well with multiple cores. That stream width is actually a generalization of mapping, right? You imagine mapping over a stream. SMAP takes a function, takes an event, and transforms into a new event, and then applies it. And map is a generalization, is a specific instance of reduce. SReduce will take an accumulator in an event, some state, and it will combine them over and over again, emitting the reductions as it goes. So that way, you can build things like change state. You could do run length compression. You could find correlations over time. Change state will detect any change in the state of an event, but it could be any function. You could detect a change based on metric, detect a change based on some transformation you apply, maybe customer ID. You can differentiate, but you can also integrate. Counter does that. So this way you can transform between those two kind of big ways of representing data, right? Routers love to have counters for their packets and their throughput and whatnot. A lot of other services expect to see relative deltas, so you can use differentiation to get to that point. Where you want to fill in values, you can use interpolate and fill in. These will repeat anytime you see a hole in your data. So if you're receiving events and they stop for a while, you can emit the last event every 5 seconds or so. This is really useful for people like Graphite who expect to receive an event every time slice. And if you have a sparse event, like maybe somebody makes a comment on a web page and it's only getting hit every couple minutes, then you could fill in zeros for the remaining time. Throttle and rollup help you address the problem of too many alerts, alert fatigue. Throttle drops excess events, and rollup says, okay, every hour I'm going to be allowed to receive 5 events. But it will aggregate everything after the first 4 events into a big bundle and then send that along. So you'll get an email at the end of the hour that says, hey, I saw 6,000 events, and they were on these hosts involving these state transitions, and here's the full log. You can take percentiles, right? So take all of your API usage data. Every time you handle a request, you emit an event saying, here's how long it took. You can sample those together and get, say, the minimum, median, 95th, and 99th percentiles out of that. This is really useful because you can't actually compose percentiles after the fact. Like if each API server instruments its percentiles separately, it's not correct to just average them. You need to take some sampling of the original underlying data set. New in Riemann 020, you can find top K. So this is a streaming top K algorithm. It maintains in the index a list of the top events by metric for each hosted service. So if you wanted to know about the top, most expensive API calls, or the consumers, your customers, who are using the most data from your plan, you can do that with this. Computing windows is easy too. You can say fixed event window, fixed time window to get chunks of events that don't overlap, that are sort of disjoint. And you can use moving event windows to say, give me the last 5 events together in context. And that way you can apply transformation, smoothing functions, that sort of thing. And then there's coalescing in terms of space, right? Not just over a single stream in time, but saying, what is the current state of the system? Coalesce will tell you about not just the single event, but every event it's seen so far that is recent or valid. What's the current maximum CPU? What's the host that's using the most disk space? What are the problem children in our infrastructure? And because this is Lisp, we have macros. Macros let you write things like by. By service establishes a copy of the rate stream for each distinct service it sees. So you have one rate for service foo, one rate for service bar, one rate for service baz, and we'll just keep creating copies of these and dispatching them with its own routing table. So rate 5 here is actually not evaluated normally. It's captured as an expression then used to generate functions later. New in Riemann 020, we also have streams for asynchronous behavior. You can defer operations onto a thread pool executor. If you wrap a stream in async queue, it will establish a new thread pool executor, some sort of probably bounded queue, maybe a linked blocking queue, and push all your work onto that. This is really useful when you don't want to guarantee delivery of events, but make a best effort. So if you're forwarding to an external service, maybe over HTTP or via the network, Riemann does everything blocking by default. It will not acknowledge receipt of an event until every stream has had a chance to process it. So if you use async queue, it'll return immediately, and you won't know whether it completed or not. But you can also get much higher throughput because you don't have to wait for that external service to come back every time. So again, you're always drawing a balance between back pressure and latency in this sort of scenario. The general principle here is that you aggregate all kinds of metrics, not just application instrumentation, not just network instrumentation, but things like exception logs. Every time you get an exception, I can get an email about it, and then I'm actually responsible for going and fixing those things. Every time my system fails, like Laura mentioned, I can add a new check, a new type of detector that knows how to handle that thing. So my system only fails in novel ways. Or I can instrument business metrics, things like customer acquisition. What stage of my funnel is losing the most customers? This turns out to be CEO catnip if you do it right, because these graphs are live. And then you forward all that data after you've processed it out to other systems, to email, Graphite, Labrato, PagerDuty, probably Datadog later, actually. And then there's a dashboard that will visualize the current state of the system in streaming fashion. You can push about 2,000 events per second through Riemann's dashboard. So if you start talking about like 5-minute scale monitoring and how long you have to wait to see something appear in your Nagios dashboard, it can be sort of a transcendental experience to look at a dash and realize that this is top, updating once every 10th of a second or once every second, and it's across 200 nodes. In addition, to handle large workloads, you can compose Riemann servers together. So if you use the forward stream, it can take a TCP or UDP client to another Riemann node. So you can run Riemann for each, say, cluster or each data center, and you can combine them, aggregate them into a central overview. This way you can have sort of a low-resolution overview of your entire network topology, all the applications everywhere, and then you can drill into specific Riemanns to address specific problems. All of this is predicated on this idea that configuration should actually be code. I recognize this is controversial, but I argue that in situations where you have a lot of complexity and everybody's infrastructure is different, and I think that's usually the case for operations, you're going to have complex config. and you better be equipped with the tools to actually approach it. That means naming things, breaking problems into parts that can be composed. You're not just hopefully hacking things together, but you're actually thinking as a designer about how are these parts going to interact and be reasoned about in isolation. How can we test them? How can we isolate them? So not only can you include config files like you can in almost any configuration language, but you can logically namespace them. You can say namespace, mycorp.amqp to store all of your ActiveMQ code that handles your instrumentation for your particular queuing setup. And you can define a new variable, alertOps, which is this roll-up stream, and then you can reuse it in different places. So your config should always be built up of small pieces which are easy to understand, and you do that by naming things. All of this is compiled code, right? This is a list, but the compiler is available at runtime. So if you kill Riemann with a SIG-hub, it'll actually recompile your code and transparently swap it in, and it will do this without breaking TCP connections. The one downside to this feature is that I can't reach into individual closures and preserve their state. So you will lose any state inside of streams, but the index state will be preserved, and any active TCP connections, UDP connections, those sorts of things will stick around. And there's this whole system for dealing with equivalency and lifecycle. The reason all this complexity exists, right? The reason I'm asking people to use this crazy language to talk about their operations problems is because in every computer system, there's a trade-off between flexibility, extensibility, and rigidity. If you solve a problem really well and you encode your assumptions about the world, the way services are organized in a strict way, you end up with a sort of rigid but also easy to use system. So Nagios, right, incredibly easy to set up, relative to Riemann. It is a simple model. People understand polling, they understand writing plugins. It does all of the host downtime management and state management transitions for you. But because its assumptions about the universe are rigid, it says hosts change rarely. And so people write programs to generate Nagios config files and reload them because it's not designed to accommodate a flexible infrastructure. The same thing goes for almost every existing infrastructure product. I think you reach these boundary points when you can't push any further. And I wanted to give people an option which was so permeable, so extensible that they could adapt it to handle almost any kind of monitoring incident, and in particular, to glue different systems together. So my goal is to make complex problems actually tractable, actually solvable, without writing a ton of in-house code, at the cost of having to deal with some Lisp or having to deal with some functions here and there. So, what the hell is this thing? It's a complex event stream processor, right? Like Esper, it views the world as being composed of discrete events, and it processes those events in some pseudo real-time fashion, and then emits them out. And it's designed to unify different systems. I keep the scope of Riemann quite small. It's an event stream processor. It doesn't handle storage, doesn't handle visualization. All of that is a separate concern. I try to integrate with systems that do these things well instead of replacing them. And it also has the goal of being as low latency as possible and as extensible as possible. With that in mind, many people come to Riemann and they expect it to be things which it is not, and it's not documented that it's not these things. So I want to state it publicly. It's not a queue, just like Redis. It is not a database, just like Redis. It's actually very akin to Redis in the sense that this is a transient store. It's fast at a certain type of operation. It provides you no transactional semantics between keys necessarily in a concurrent fashion. So it's okay to lose an event. In the same way that in Nagios, right, like a check might fail once, but it would come back and get it again. In Nagios and in Riemann, you architect your systems such that events are constantly being received. They're always flowing through. And so even if the system hiccups for a second, if a TCP connection drops, Riemann can't guarantee you that particular event is received fully. It tries its hardest, but it can't guarantee it. But if your system is architected to send events constantly, the next second you'll figure it out. So in practice, I think it works pretty well. The other big constraint is that it is not a distributed system, which seems a little weird, right? Because I'm monitoring distributed systems, and so of course my Riemann should be distributed as well. The reason it's not is because it's a hard problem. Riemann has a very different kind of constraint from a database, right? In a database, you can have eventual consistency, you can have transactions, and you're allowed to hang some of the time. You can wait, because it's okay for your data to be consistent 5 seconds from now or 5 minutes from now. In Riemann's world, a second is quite a long amount of time. And if I ever wait longer than 5 minutes to page you about a problem, you're screwed. So I have to balance the latency problem, wanting to get to people and tell them things immediately with correctness. In Coda Hale's terms, Riemann sacrifices harvest, not merely making a cat trade-off, but actually saying it's okay to lose or misinterpret some data. It's okay to send duplicate events sometimes, to make multiple pages, so long as we make sure that we're doing the right thing most of the time, and we try to never give you false positives or false negatives. So, with that in mind, when your monitoring problems are complex, as I think they are, Riemann gives you some flexibility to adapt, and it may be worth checking out for your systems. Thank you for your time.